Please join us for a panel discussion. We're going to have a panel discussion on NSCI. That's Obama's executive order. And this nation of the USA has put a stake in the ground. We're going to build an exascale system. And we've got a great panel. And we're going to bring our first speaker up. The way we're going to run this is each of the speakers will give a short presentation on what they do in supercomputing and how it relates to NSCI. And then we'll seat them here, and we're going to ask for your questions. So I'm Rich Brueckner with insideHPC. I'm a journalist. This isn't what I do for my day job. I usually just write stuff. But I'm very excited about NSCI, and I think the future of supercomputing in this country. And I'm just really thrilled with this panel. My job will be to ring them in. I think it's going to get kind of a lot of horseplay. I'm worried. Yeah. So with that, Dan Stanzione, if you could bring your slides up and tell us more about TACC. You're the host man here. All right. I don't know if that's on.
Thanks. All right. Thanks, Rich. I'm actually not going to tell you more about TACC because I've done that 10 or 11 times this week already. And if you'd like to know more about TACC, just go over there. And you can find out more about it. So, but our topic for the panel today is how the National Strategic Computing Initiative, or NSCI, will make HPC more accessible to everybody. I do want to start, okay, where's the advance? Yeah, you just run them for me. We are the host here. As it turns out, we wear these hats every day. It's not just a Dell thing. Everyone at Dell or TACC wears these hats all the time. And you're welcome to too. But you are just a few miles from us, so welcome to Austin for all of you who aren't from here. We encourage you to come by and visit. We've been running buses back and forth to TACC. If you'd like to come see us, just drop by the booth and say hello. If you'd like to come see Dell, they should have a bus somewhere going to Dell. And if not, now I put them on the spot. So, but anyway, we're happy to have everybody here at SC15 to talk about this, and come by and see us if you can. So, the NSCI. So if you haven't heard too much about this, and Sue has, about the National Strategic Computing Initiative, it really has four primary broad aims, right? So to deploy and apply exascale technologies broadly for economic competitiveness, to foster public and private partnerships, which I'm sure is what Merle's going to focus on in his section of the talk, to adopt a whole of government approach instead of the every piece of government gets their own booth at supercomputing approach that we've taken to supercomputing so far, and to have a comprehensive approach to transition HPC into R&D operations. So, did I miss a slide here? So the topic is how the NSCI is going to make things more accessible. And
Dan,
I'd like to begin.
They're having trouble hearing you, so you got to eat the microphone.
Even closer.
Yeah.
It is the 10th talk of the week. No one has ever had trouble hearing me before. Tom knows. All right, so why do we assume, first of all, that this is going to make things more accessible? The goal of the NSCI is to deliver an exascale machine. And if you look at the broad trends, bigger systems and accessible has not been our history very successfully. We've built petascale systems today, or 10 to 100 petaflop systems today, and there's really no evidence that they're more accessible than terascale systems were 10 or 15 years ago. And if you look at the ongoing trends, that's concerning. And yes, there is the word accessible somewhere in the NSCI itself, but it actually is the fourth strategic theme in a program that has 4 principles, 5 objectives, and 5 strategic themes. It's number 14. So it's not something I would count on. So I would say, from my perspective at TACC, and I think from a lot of the university folks here, there's some really encouraging things, what's going on in the NSCI. And if you dig into it, there are 3 lead agencies: the Department of Energy, whose essential job is to procure an exascale machine, and the DoD, whose role is in analytics for a certain other 3-letter agency within DoD, use your imagination, and then the NSF role. And the NSF role has 3 parts, and I think it's the most interesting of the various roles out there. It's the broad ecosystem of computing, and we can hope that's more of the Track 2 type systems we've seen, maybe at a larger scale with more awards. It's the workforce piece. How do we, in terms of accessibility, how do we build people who know how to use these things? And I think that's a great role for the NSF to have. And then future models of computing, which is the basic research into doing that. And to me, that's a lot more interesting than running a procurement program for an exascale machine. So we're excited about the role that NSF is going to have as an NSF center. Now, of course, the danger in all of these things is they become recolored money. There are programs that have sort of all these names now, and sometimes they just add them up and say, here's what we're doing. Isn't this a great new initiative? And so That's, I think, the pitfall that we're all worried about it. But it does seem like we have, as NSF centers in the university space, the most interesting role in growing towards exascale. And that's awesome. But I still think for accessibility, our main topic, and I think this is the last slide, Rich, it's up to us, right? The great thing we're going to have with the NSCI is there's increased attention from the government level, hopefully increased coordination among agencies. We've tried to do things between NSF centers and NOAA or NSF centers and NIH. Never quite works out right because the mechanisms, the impetus from the top just isn't there. And hopefully this will give us that impetus, and hopefully there'll be substantive new funding streams for us to attach to go after that. But I think accessibility is up to us, right? If you look towards exascale systems, the current trends are going to continue. The machines are not going to be simpler. They're going to be more complicated. They're going to be much more parallel. They're possibly going to have heterogeneity involved in them. They're going to have much deeper memory hierarchies, much deeper storage hierarchies. You're going to have to do cache blocking at 10 levels. So they're likely much harder to program. But complexity for programmers doesn't mean it's going to be complex for the end users to deal with. If you look at our makeup at TACC today, most of our big users are still people who SSH in, but most of our users come to us through the web one way or another. About 75% of them are strictly end users, not programmers of the machine. And we've made a huge commitment in building REST APIs and other things to make that level easier. And I'm not sure the NSCI is going to directly support that, but hopefully it will give us the resources that are essential to what we need, but accessibility is still going to be up to us. So, thanks.
Thanks, Dan.
That was it. So.
All right, great. All right, our next speaker is Michael Norman. If we could bring up Michael Norman's slides. All right, buddy.
Okay, well, I'm not going to repeat a description of the NSCI program. Dan did that very nicely.
Michael, you gotta be real close with the mic so they can hear you. Yeah.
Really close with the mic. Okay. So I'm going to take the flip side of that argument and tell you all how it's going to be a paradise of accessibility. And I'm going to do that by talking about what the situation is today in HPC and arguing that it's just going to get bigger and better. So let's think a little bit about the last 40 years of supercomputing. I've been using supercomputers for 40 years. And in those 40 years, I can only remember 2 federal initiatives that changed the conversation. One was in 1991 with the National HPC initiative, which launched the Grand Challenge projects in many agencies. And the other is the one Obama just announced in July. And if we think about what the world was like in 1991 and what happened in the subsequent 20 years in terms of access, I'm going to argue that the same thing is going to happen with this initiative. And the reason is fundamentally the Branscombe pyramid, which some of you know. This is a diagram from a report, 1993 report, chaired by Louis Branscombe, who was talking about from desktop to teraflop, exploiting the U.S. lead in high-performance computing. And the point I want to make is equipment at every level of this pyramid is built out of the same technological components. So whatever you do to raise the top of the pyramid, you're just going to make the pyramid taller, and there's going to be more levels in between. Here, there were 4 levels identified. I think today you could argue that there's 6 levels. No one's written that report. But I would argue that we have never had more access to HPC than we have today, and it's because we have a vigorous technology base, we have vigorous spending by the federal government at the top. And everything below that comes more or less as a consequence of that leadership pursuing the top. So let me talk a little bit about access to HPC today and what my center is doing. And I'm going to make the argument that the same can and should be done with the exascale technology. The technology is the important thing. It's not the system. So if we look at the Comet system at SDSC, it's a system that we architected for access for the long tail of science, small to medium-sized jobs. And one rack of Comet is 70 teraflops, which was the top of the pyramid in 1993. So now, sort of a middle-scale supercomputer, which is a 2 petaflop system, has about 100 teraflops in a single rack, and we make this available through web browsers to the long tail of science users. So that's what we've accomplished as a community in 20 years. So Comet explicitly targets users in the base of the pyramid, but that base only exists because of the pursuit of the high end. And the rest is a kind of a trickle-down effect that benefits everybody. And there's no reason why this can't happen, especially through the NSF auspices. As Dan correctly pointed out, the NSF really does own that access mission. And I hope there are people from the NSF in the audience listening to this. Ease of use is the name of the game. Making HPC easier to use through web portals, deploying familiar desktop applications for people who don't normally use supercomputers like R and MATLAB. And the newest cool thing is Jupyter Notebooks. We have the ability to launch Jupyter Notebooks on Comet, on the Comet compute nodes, returning an interactive session for one or more compute node, depending upon the size of your job. That's going to be revolutionary in terms of providing access to HPC. The other thing that is happening, and we all know this, is big data analytics is discovering that HPC platforms are actually better in terms of performance than white box clusters. And so there is this convergence of HPC and big data analytics at the architectural level. On Comet, we have the full big data analytics stack running inside of a Jupyter notebook. You can fire up Spark from a Jupyter notebook, suck in your data, and do big data analytics much faster than on a white box cluster. So this is something that is happening now. There's a lot of skepticism about whether the NSCI is really going to pay attention to big data analytics. I think the answer is yes, because I know what's going on in the DOE labs. They are architecting converged architectures to deal with both modeling and simulation and big data analytics workloads. So that's going to be there as well. So finally, and this is my last slide, let me just return to the question that I was asked to address, how the NSCI will make HPC more accessible to all. It's really, in my mind, by advancing the technological base, not just the hardware, but the software as well. That's really the valuable thing that will be pursued and developed through this initiative. But a little more technically speaking, the interesting action is going to be at the node level. What is happening to those nodes is going to be amazing, and we're already seeing some hints of that with the 3D stacked memory and stuff like that, NVRAM. The nodes are going to be vastly more powerful and data intensive than what we have today, and those will be available to the individual researcher in their laboratory is at the bottom of this pyramid. By pushing the envelope on energy programmability and accessibility. Again, I do think the NSF owns the accessibility charter. And if we just think about what the Branscombe pyramid of 2023 might look like, and that would be a fun exercise for us to do on a napkin in a bar tonight. Maybe there'd be 10 levels, I don't know. We're going to have exascale leadership facilities at the top. We're going to have petaflop departmental clusters, and we're going to have teraflop smartphones talking to the other things, right? And so it's going to be quite an interesting ecosystem, and I'm looking forward to computing on those systems in 10 years. Thank you.
Thank you, Michael. All right, our next speaker is Merle Giles from NSCA. If we could bring up Merle Giles' slides, we'll be good to go.
That would be NCSA.
NCSA? Well, NSA, I thought. No,
yeah,
it's NCSA.
You're in there somewhere.
Yeah,
you're in there somewhere.
Thank you.
But
thanks, Merle.
Dr. Norman, I respectfully disagree with your statement that technology is the answer here. I'll stop short of calling you crazy, but yeah, I respectfully disagree. So, it's not about the technology, it's about the impact, and I'll tell you why. Economic competitiveness. That's equal to scientific discovery on bullet number 1. Principle number 2 says, let's get public-private stuff going on together. And oh, by the way, some of that definition is industry and academia. Dare we suggest that, right? I've got to press this harder. So you did address the make HPC more readily available, let's improve developer productivity. But if we go back to this economic competitiveness, I want to state that if all we do is what we've done the past 30 years, we will fail. Here's the State of the Union address just this year. It doesn't say we need more technology. What it says is we want to cure people and we want to get the right treatment the first time. That is the impact. That's where HPC lives, because the big data systems can do that. This will pull the technology into the mainstream of touching product. If we don't touch product, the economic development will fail. The economic impact will not be there. This is a government slide that has been shared that I like a lot. So this funding on the left for basic research tends to come from government and universities. We need that. That's where HPC has lived for 30 years. I would submit, Michael, that the other game-changing event was 1982, when the NSF centers were actually first begun. So that did make a difference. We had 5 of those centers. The access changed dramatically. So if governments and universities fund the left side, the right side is funded by companies, venture capitalists, and so forth. That's the product side. We understand the left side pretty well. That is where HPC has lived for 30 years. 40 years, perhaps. What's missing is in the middle, which is the valley of death. There we go. I'll call that the valley of death. So the theoretical and basic research on the left, real commercialization on the right. What must happen in the middle? We got any companies in the room? Dell's got to make product. Other companies have to make product. In order to make those things, we have to de-risk, we have to prototype, develop, optimize, and then I made up a word. We need robustification. There is no funding in the middle. Very little funding in that middle. So if we look at TRL 1, that's basic research. TRL 2 is applied research. 3 is proofs of concept. 4, 5, and 6 are what I call the 3 Ds. Development, demonstration, deployment. Then we make things and the product goes out the door and off the dock at TRL 9. That middle space, that gap, needs attention. HPC needs to be in that space in order to touch product. The way that HPC looks is more like a sandbox. We need to help companies de-risk and lower the uncertainty that comes after the discovery. God bless the discovery. We need that. We need to understand the fundamental tenets of science and engineering. But if that's all we do, we will not touch the product. So NSCI says, thou shalt have economic impact. So we've got to pay attention to the business models that can get us there. So I usually get shot when I say these kinds of things. I'm wearing the white hat, so, bear with me here. But we can't just do HPC in an allocation model with a business model that has been around for 30 years. We need to mix that up and change the access even more than what we have today. We need a play place and a sandbox to develop the code and actually have rapid prototyping and fast failure in the middle. And we do not deploy HPC in that way today. I got at least 2 nods out of the crowd saying that. So let's see here. I'll get back to, oh, those are all my slides. That's my story. Really, it is. I like this the most. We have got to touch product in order to have the economic impact. That's where the revenue comes. That's where we get cost cutting. But today, so let me just suggest this, and I'll leave it to you.
Yeah.
Today, we don't have a place for the world's largest companies to actually step into a space where they could do 10 or 100x in the mod sim space. They don't have persistent access. If they have to pay for commercial code licenses to get it done, it's a non-starter. It will not happen. If we have non-starter behavior and we can't help those folks, we'll never get off the ground in bringing 100x HPC to industry. That's my story, and I'm sticking to it.
All right. Well, thanks, Merle. All right. Dave Lifka from Cornell, he recently was named interim CIO. So congratulations, Dave.
Thank you. Thank you. Can you hear me okay? So
hard to hear you.
Better?
Yeah. Thanks.
Okay. So I thought what I'd do is tell you a little bit about Cornell. So unlike the previous 3 speakers, we're not a national service provider. We're not heavily funded by NSF to provide accessible resources to the
They're
research
still
community.
having trouble here. You got to really eat the mic. It's as loud as it goes. Thank you.
Okay. Better? So at Cornell, we have a cost recovery model for HPC. And we charge our researchers to use the resources that we have. And we've been doing this for 8 years. So people say, well, that's crazy. How can you do that? And, well, we do it because if we don't provide things that they want, we won't be in business. And I think it's important to understand that what we did there was we followed industry trends. And a current industry trend, which wasn't mentioned yet, is cloud. And a lot of people here will tell you, oh, that'll never work for HPC. And I will agree on one hand. I don't think it solves all HPC problems. So the systems that you heard about previously are very specialized, Blue Water, Stampede, Comet, things like that. They're very important. But there's this new growing paradigm which industry is driving, not us, which is the use of cloud. It's going to require new programming paradigms. It's going to require new technical skills from our staff. And that's really important when we start to consider workforce development, which is part of the NCSI strategy. How do we address that? How do we make sure that we leverage resources that are really complementary going forward and are sustainable, right? So you're not going to see more centers pop up given the current budget funding model. It's just not going to happen. In fact, the opposite might happen. And even with NCSI, we'd all like to believe this means funding that's in place for a long time, but we all know that the reality is every year Congress has to change in priorities, funding ebbs and flows, and we've got to make sure that this NCSI initiative has some sticking power, not just a presidential mandate because it sounds good this year, but actually we help as a community demonstrate why it's important together. And it's not just the big centers, it's all of us. So that's one message I'd like to say. I think there's some real opportunities coming from Exceed to help broaden participation. One of the things that, and also from NSF in the terms of DIBS awards. So we recently won a DIBS award, which is Data Infrastructure Building Blocks, in which we proposed a cloud federation of very, very modest amounts of hardware, but really a model for sharing resources between institutions for data analysis and for small-scale simulation as a way to reach more people. So maybe it's not even on the Branscombe pyramid, but it's an important component because if we don't get the tools and the software in the hands of students and even staff whose skills have lagged, we're not going anywhere. And so I think, everything you heard before I will agree with, but I think we have to also focus on how do we get more engagement. So accessibility is not just giving people access to a big computer, it's how do we get more people engaged in this process. How do we do training, which I think Exceed is doing a lot of, and I think that's important. And how do we understand and embrace new paradigm shifts in computing for big data, analytics that are complementary? So I think that's the sum of my comments. So.
Okay, thanks, Dave. Oh, great. All right, if we could have our panelists take a seat up here. We should have an extra microphone for you. All right. So you can share with Michael there, Merle. All right, guys, we're going to open this up to questions from the audience, but I want to start out. When I first heard about NSCI and saw the presentations, I was really excited. For the first time, the United States, the agencies that all buy these supercomputers are going to try to coordinate under one roof and really talk to each other and work together, right? That's the idea. But I'm a journalist. I write about HPC, and I watched all the headlines that day, and they just picked up on one thing, exascale. And I started reading the document, and there's just a lot more in there, as Merle started to bring out. And one of them was the big data analysis, right? And the usability. So headlines are very powerful, but this thing is not about exascale just, right? And I was wondering, Merle, could you comment, because I mean, you're the one that I think was getting me on this horse, and I agree completely, right? So what do you think? I mean, did they put the right emphasis in there? Are the pieces in that document to go forward and be successful from this stage?
So from my seat, we need the exascale because there is an aspect of the scale that must be in place before we can do Y instead of X. So that is true. How we use it, I just chatted with somebody from OSTP here recently and said, you know what, the problem's not the tech. The problem's the business model. So yes, we love the tech. We do need the exascale, but we should not confuse or extend the business model that got us here that was only looking at research computing. We need to change the business model that will affect the access and the students and the rest of the periphery around that in order to do the software development. We cannot be successful at NSCI if all we do is build a big machine. That is necessary, but we must also look at the business models that will be the result, that will actually drive the impact.
May I respond, Rich? So, problem with closed doors, then we get
Is
this
that work?
feedback loop.
Yeah.
So Merle, I don't disagree with much of what you said, but there are a lot of initiatives. This isn't the first one. They don't come out of nowhere, right? They didn't wake up and decide to do this one day, and this is the exascale plan. Right? And that was the genesis of it. That's where it was put together.
Yeah.
And there's lots of other words to make constituencies happy, but it's the exascale plan. So at its core, it's been brewing as that for several years to get to where it is today. Also, there's the document, and then there's the implementation plan, and it went in last week, I believe. So last Friday? Yes, it went in last Friday. So the time to advocate for change was a while ago
Gotcha.
in the way that this works. So there are a lot of things that need to happen. They don't all happen under one initiative. We have a brain initiative too, and yet we still think this way over the last couple of years. So, I am unconvinced that this will spread into the gaps that you would like it to spread into. Not that I think that that's the wrong thing to do or a bad idea, but a lot of wheels are in motion on this one.
Yeah.
You're probably a realist.
Yeah. And
Yeah, annoying.
well, help me with the realism part here, guys, because there's only, as of the new top 500, there's 80 systems that are petascale, right? 80. Last I heard, there's only about a dozen codes in the world that run at that level besides LINPACK, and most of them are high-energy physics, right? Does that help me with cancer and these other things, right? It just seems to me
Sure it
we're a
does.
long way from even making petascale widely available to these folks versus something 1000x.
You want to go first on this, Mike?
I guess people didn't understand what I was trying to say, and that must mean I didn't say it very clearly. the technology that's developed for that apex of the pyramid trickles down all the way to the base of the pyramid. And that's going to solve the access problem. Now, it's necessary but not sufficient. You also do need someone to bridge that gap that Merle talked about, whether it's funding, whether it's a company that says that's a business opportunity to go into that gap. I was just talking to the CFO of our systems, who hosts equipment at your center, and he is trying to fill that gap through assistance and, you know, a very cost-effective business model. But my point is, if we had the technology that would allow us to build an exascale system, you know, with those tremendous challenges in energy efficiency, which all translates down to the node. You have to solve it at the node level, and if you've solved it, you've probably got, I don't know, 100 teraflop board. Give that to industry, give that with software, and you will start seeing HPC being used not just at the, you know, Fortune 20, 50, but many, many more companies. So I guess, you know, it's kind of a supply side economics philosophy, which pains me to say that because I'm not of that political persuasion, but that's
you are
what
from
I'm.
California, so is Reagan.
That is what I'm saying. There's going there, and you can see it right now. You can see that there is more industrial use of HPC now than there was 10 years ago and 20 years ago. It's just going to take time.
Dan?
Yeah, so if I could echo, I'd like to agree with Mike. I think there's more like 30 codes at the petascale now, but I have two of these 80 systems. And you know, 10 years before that, we might have said that there's only 10 codes that scale to the terascale. And how does that help me? And how many of them you think are terascale today, right? 4,000 of those? You know, we run, and you also need to think about these systems as what is our aggregate need, you know, for discovery and innovation, right?
Yeah.
And, you know, Merle talks a lot about the broad set of companies and the different gaps we need to do beyond basic discovery. On our two petascale systems, you know, we have 3,000 different projects. We have 4,150 codes that have run on Stampede at this point, right? Yeah. So it's a petascale system, but it solves a lot of problems at a lot of different scales, right? And we have a lot of problems that we need to solve, and even between all the systems we have here, we don't have nearly enough for what the demand is for the systems that are out there. So, yeah, they don't all scale the petascale today, but without the systems, they're not going to scale there tomorrow. And there's a lot of things at the mini terascale that we're solving now that we wouldn't be doing 10 years ago without this sort of pathfinding and technology. So, right on, Mike.
So I'd like to prove my point. I do agree with what you've said there, but I'm not sure it's the right question to ask how many petascale codes there are. And here's why. 18 months ago, my team at NCSA took on a project to see if we could scale LS Dyna. We had a collaboration. We got input decks from two big companies. They said, I dare you, you'll never make it past hundreds of cores. We got to 15,000. Okay, that's not petascale, but we used the techniques and went to go see a buddy of mine from Barcelona to take an engineering multiphysics code, 100,000 cores on Blue Waters. Now that's a petascale code. Then we said, you know what? We need to quit blaming the ISVs in the commercial space for CAE and manufacturing and calling them a bunch of idiots. We need to really love them and show them that love. So we took CD-DAPCO and we took ANSYS Fluent. 102,000 cores for the CD-DAPCO CFD code. 129,000 cores is where we are now with ANSYS Fluent. They didn't know it could scale. We didn't know it could scale. Nobody knew it could scale. But the only reason we got that done is because we did it without permission. Yep. We broke the rules and ran on Blue Waters without asking permission nor going through the allocation process, which was on the table. We went through the back door to make it happen, and now we have petascale engineering codes, and we never knew that. So the point is, we need a play place. We need a sandbox. We need to break more rules to actually unleash this innovation engine.
I'm shocked that Merle didn't follow the rules.
Well, this is not the first time he's straightened me out on something. So, all right, so I'm going to open it up to the audience. Are there questions for our panelists? I have more questions, but you're here to learn from the experts. Who's got a question? Anybody? Okay. They're being a little shy right now. My question's about communication, right? Because we brought up the topic of money, right? This is NSCI is not funded. It's a policy directive, or is that what? Yeah. And we all know, as David said, Congress has different priorities every year. This is going to take a lot of money. Billions, I would guess, to build an exascale machine, right? But the communications I've heard so far out of this, I agree with Merle 100%. It needs to be about cancer, solving cancer, and things like that people can get their arms around. The communications I heard at first were all about co-design and acronyms that wouldn't get a senator to look up from his iPhone. So I want to bring that up. Do you guys have the same fear that we're not going to be able to sell this because it's just we don't have the right tone, the right communication, or the right people delivering the message?
We need Alan Alda.
Yeah.
No, I think that's right. You have to relate what the science is, what the outcomes of the science are for society. I think that's absolutely right.
Yeah.
But it starts with training the scientists on how to use it, and there's a whole lot of training that has to happen. And as the architectures evolve and change, it's the battlefield's changing out from under us. So I think the potential's there. People are doing precision medicine today on terascale machines, and effectively. So so the communication problem there is, well, what's going to change if we have exascale? And it's things like comparisons that you can make in human genome sequences and things like that you can't do today. Mm-hmm. And in the time that you could go to the doctor and have have your own genome sequenced and done in minutes instead of hours, days, or weeks, so that they can make diagnoses right there on the spot, which is often, if you're a cancer patient and you're sitting in the doctor's office, the last thing you want to hear is come back in 2 weeks and we'll tell you the results of your tests. Right. And those are the kinds of things that people understand. You can put in the New York Times. You can put in your online articles, and people will get it.
Yeah.
But we don't have enough of them. Yeah. And most people don't know what CD Adapco is, right? We do, because we're nerds. Yeah. Right. Yeah. But that's, how do you translate that into a real story? And I think we know how to do it, but we don't do a good job, and we don't do it often enough.
Dave couldn't agree more. That I was just doing a history lesson over in our booth a bit ago, and in the 1940s, World War II, computing came about and drove digital vacuum tubes and other stuff beyond human computers because of the need to do things quickly. There was a need for speed, for like ballistics and firing tables. So that we need to rally around the solution. We need to rally around the cancer, rally around the precision medicine, and the other things that that are the beneficiaries of the need for speed, and that can get the attention. We've got a question right here.
All right, yeah, let's here, so the camera can hear you, sir.
Perhaps to use the word we seldom hear in our industry. I hate to use the M word, marketing, but that's what this is. And it's a question of branding, of telling stories that people understand. But is NSF or the federal agencies going to take a portion of their dollars within a program like Exascale and put it towards something called marketing, which communicates to the public the value of what we do? This panel, you guys are all techies and experts, and everybody in this audience, there's no marketing people here. We pretend we're going to do marketing and outreach, but yes, you're a marketing person. You could sell anything. I'm sorry. But that's my point.
Yeah, I agree.
So I generally agree, Paul, but the week of SC sitting on the show floor is not the time to argue there's not enough marketing budget in HPC. And if you don't believe me, go over to Fogo de Chao and see which vendor will buy you dinner.
Yeah. Are we preaching to the choir here?
But I understand your point, definitely.
It should be
absolutely.
On. I think it's on. Go ahead.
It's not so much
absolutely, we are talking to ourselves.
It's not so much the marketing budget. It's actually the focus of the marketing. Right. And that's most important, because marketing is such a catch-all phrase. And if you want to focus on medicine, manufacturing, military, the 3 M's, that's what you've got to do. These supercomputers are going to become an app. You've got to bring apps out of this, and apps that people can use.
I agree.
What did you just say? You said manufacturing, military, and medicine. Hey, this guy's a born marketer right there.
Yeah, yeah.
I think 3M might be
Alliteration is
trademarked
goodness.
Let's see, I just want to make a comment. Precision medicine does not require exascale. It's getting roughed out right now on fractions of petascale systems.
Yeah.
So let me tell you about a project that just started in San Diego. We're in the middle of tech, biotech Mesa. And we have Rady's Children's Hospital, which has the largest cohort of children in California. And they're right across the road from Illumina. You've heard of them, the sub $1,000 human genome. Well, I'll tell you, that's a load of crap. You only get sub 1,000 if you sequence 100,000 genomes at once.
Yeah.
But if you want to sequence one genome, it's $30,000.
Yeah.
And so we're working with Rady's Children's Hospital, whereby the kid and their parents walk in, they take 3 blood samples, they sequence the parents and the kid, and they want to turn that around in 24 hours. That's their requirement. That can be done on one rack of Comet with the right software and the right policies for getting the job through to the head of the queue and so forth. So we're doing that. And that revolution is not something you will hear about in the newspaper. It's just going to happen little by little by little. It'll be emulated here, emulated there. People will scale it up, and before long, you'll say, wow, a revolution just happened, but it's been going on for 10 years. So,
But that's precisely the problem,
what's the problem?
that it trickles out and that no one really hears about the impact. And
But
so
that's the way progress happens.
that's in a scientist world, but not in the New York Times world, right? And so
no, someone will eventually write an article.
right,
John
but the
Markoff
problem is
will
that
write
in
an
the
article about
In the meantime,
this.
Congress is wondering what the hell we're doing with their money.
This is good.
Right, and
Yeah.
hopefully John will have written that article by the time they ask that question.
So, Michael, we're pushing petascale with some Alzheimer's work on Blue Waters right now. And it is the A-B connection, the collaborative knowledge that comes from actually combining 2 segments of Alzheimer's that actually drives that scale. And the first round was going to put out 500 petabytes of data. So it's like, oh, okay, let's go. We can't do that. So let's go back and rejigger this thing and try it. So this was kind of the innovation sandbox. We needed to play to figure out how to rationalize the work that was actually way too big. So we've seen some success where it's not exascale, but it's not terascale anymore. We've gotten beyond that because we can attempt and try to do things that were not possible if we didn't have the machine.
So back to your question
Merle,
about communication.
you pick big problems on purpose because you have to justify the existence of Blue Waters. I'm saying scientific progress doesn't always require the biggest hammer.
No, agreed.
Okay, Dave.
So one of the back to your question of communications. One of the
Yeah.
things that we're challenged with in this community, the community that's on the show floor, is we're not good in planning the way other disciplines are. If you go to the astronomy community, you go to the physics community, you go to the biology community, they know what their goals are, and they have a 5-year plan, and they know what their requirements are. And what do? We chase our tails wondering how we're going to help them after the fact. And so we're not communicating with our customers, so you can call that marketing or not, but we're not. Some of us are, the ones that are successful are, but it's not universal.
Yeah.
And we have to do a better job of that. And we have to be then able to articulate how we enable their success. And until we do that in a way that you can pick it up, an average person can pick it up in the newspaper and understand it, Congress won't.
Yeah. Okay. Did we have another question from the audience? You were going to say something. You were jumping in there. Yes. Okay, go ahead, sir.
I actually agree with you very much so. But the other object here, I think, is trying to establish some speed. How do we get this from A to Z? And I think to do that, you've really got to focus on getting your message out. And often in the HPC market, you talk to the professors, and you ask them what they're doing. Well, we're doing science. It's always science.
Yeah.
There's never something specific that's got a conclusion at the end of it that can bring some dollars to the market.
Yeah.
And I think you're right. If you can't come up with a good explanation of how you're going to do it, you just don't get the money.
Yeah.
And the money is what you need.
Great. Thank you. Yeah. So my next question is about people, right? And we have this discussion, seems like every year. How do we get young people interested in doing HPC? Because it seems like the brightest minds are going to work on search algorithms at Google, right, or Facebook. And the student cluster competition seems to me to be a great start, right? But I don't see it happening in other computing kind of environments. Like, there's lots bigger shows than this out there, guys, right? So do you agree? Is we're going to need lots of smart kids parallel programming to get this machine to do what it needs to do, right? So are we doing enough there, and what else could we be doing? Dave, yeah.
Death to MPI.
So just before this meeting, Sue and I were having a meeting with IDC, and their answer is, well, you got to get the schools to teach this and put it in their curriculum. And you know what? They're not gonna. They're not gonna, because the curriculum's already overloaded. The students already have too many requirements, and they'll pick this up on the side, but they're not gonna. There's very few that have the time to take it. So I actually think that part of the solution, not the only solution, is internships. So if you're a Cornell student and you learn all the theory and you learn all the processes and all the ways you do solve problems, what you really need is some place to go out and try it.
Yeah.
And Facebook is really good at this. Apple's really good at this. They excite the kids. They think they're working on cool problems over the summer. They pay them well. And then they come out and they're really good engineers doing what they're doing.
Yeah.
We don't do that.
We don't.
And the reason I'm here today is because Argonne National Lab did that for me when I was an undergrad. I had an internship.
Yeah.
I didn't study HPC. I don't think HPC was even known in 1980.
Well,
right?
yeah. I mean, on that note,
It was still moderate performance computing back then, Dave.
do you guys even teach Fortran anymore? Because that's
We
what a
do.
lot of this. You do?
Yeah.
Okay. Yeah.
Yeah, we do at UT.
Yeah.
But so I don't totally agree, Dave. I mean, career pathways are obviously important, but to your initial premise, and actually to your initial premise, Rich, I don't think people going to do search algorithms at Google is a bad thing. And frankly, I'm not convinced it's not HPC. I think, Mike mentioned the convergence of big data in HPC. There will be the convergence of machine learning in HPC, which is almost this, but not quite the same thing. But it turns out there's really only a couple of ways to scale up architectures. And eventually they will find their way back to the true path and do things in the way,
Yeah.
there's only so many ways to arrange a million processors.
Okay.
Well, we can do the math on that. We're computing people. But
Yeah.
nonetheless, I think career pathways are important, but there's constantly the argument that the curriculum is overloaded and we can't teach it and add more stuff. Yeah. We're at 4 universities here. Raise your hand if you've added a data science program at your university in the last 5 years.
yeah.
So
Yeah.
I don't know of a university that has not, suddenly cropped up a master's of data science in the business school, the information school, maybe the school of government, in engineering. We kicked up the department out of the math department. So when there is a market to drive it, and
Yeah.
I would argue that data science, as I think Mike would argue, is another just side of the HPC coin in a lot of ways. As soon as the money's there, the programs follow, the training follows, and really there's 2 things that draw people in. Money is one, but
Yeah.
we're not all investment bankers, fortunately. So there's obviously some other things too.
Yeah.
And the mission. And we've had much more success when we connect, as we talked about on the marketing angle, connect HPC to the mission. If you say, we're going to teach a course in high performance computing that's hard, if we're going to say, we're going to teach a course in cancer informatics that's not so hard to sell as a mission that folks will be attracted to.
Yeah.
And we could always do more, back to your original part, but we had a couple of great summer experiences with camps this year. One that was sort of a general high school camp, one that was just for girls that we ran, both of which were full and oversubscribed. The cluster competition is great, but I
Yeah.
increasingly worry that it's whoever can talk the vendor into the most hardware wins. Arguably, that's the same skills we have working at the centers, so maybe that is a useful thing to teach people,
Yeah.
but I'm not sure it's a technical skill. It's a skill, but it may not be a technical skill.
Yeah.
So what we did in the summer camps is we gave everybody a Raspberry Pi at the start of it. And we taught them to program on it during the week. And at the end, they all built a cluster of their Raspberry Pis and ran Graph 500 benchmarks.
Yeah.
And you'll see a couple of them on the list. And it turns out number 4 on the Green Grass 500 list is the high school girls at TACC running their cluster of Raspberry Pis. Which means, first of all, if you're below 5, you lost to some high school kids and some Raspberry Pis. So do better.
Okay.
But secondly, and then they all took their Raspberry Pis out of the cluster and took them home and kept them to
Yeah.
sustain. So, but connecting to a mission will go a long way in this, and the pathways will form when the opportunities are there.
Yeah.
So,
Okay. I would like to just go round robin here. And Merle, you started this, but what we must do to be successful. Give me the one or two things, or the thing, you know, if we don't do this one thing, this ain't gonna fly. Yeah?
So I want to actually comment on this student issue down here, and I believe we need to do two things, and
Okay.
one's sort of bottom up and one's sort of top down. We can work through the incumbents to perhaps add courses and some things like that, but we also need to think, and this is the business model approach, we need to think in other ways that are disruptive. And so I would posit that HPC is not a conversation that's happening in the boardrooms today. Big data is. And the biggest data access to the boardroom today is SAP. We have the ERP systems, the decision-making systems that are getting into the boardroom and the C-level inside these companies. HPC has never been there. So we need to change that business model a little bit, adapt in ways that have, I mean, part of this is a language thing. Maybe we don't reduce it all to just marketing, but there is a communication thing here that HPC, if it's the whole daggum triangle, it is really compute and data. It's some other, we can still throw some other, but we need the dialogue in the boardroom, which is not the normal path, but if we get the boardroom to decide that they need things, they will pull technology into that space. So we have a supply side and a demand side. We need to work them both.
Great. Michael, what do you think? What do we need to do to be successful for NSCI?
Well, the 3 lead agencies need to do what they are charged with doing, and I have no concern about DOE and DOD.
Yeah.
It's the NSF that I'm concerned with. NSF really is charged with, you know, the fundamental research on new technologies that will go beyond Moore's Law.
Yeah.
And the new algorithms, discovery using new algorithms, and the workforce side of things. The NSF really has to do that and do it well. I don't see any signs that that's going to happen at the moment. But, you know, sometimes it takes a while for the little green shoots to come up through the ground so that you can get a sense of, you know, of optimism. But that's what we have to do. We have to do the training, as Dave says.
Great. Dan, your
so
thoughts?
I agree with Merle and Mike, but let me take a slightly different tack. First of all, let me change your question just a bit, Rich. You asked, what's the one thing we need to do to be successful? You know, part of the NSCI should be the acknowledgement that we're already successful, right? We launched $60 million in new projects last year. We're doubling the center about every 3 years. I don't see that stopping. We have the attention of the administration, a new federal level initiative. We are successful. So the question is, what can we do? You know, what are something we can do to grow even more? And I would, picking up on Merle's language theme, I would just say that right now machine learning is already a much larger market than HPC. And if you look at the most widely used machine learning library out there and you get down to the core of it, it runs LinPack. It solves linear equations in the core. So what don't we do? Why isn't machine learning also HPC? We don't speak the language. So one strategic thing we should do is learn the language of machine learning, bring them into what we do. We'd be triple the size we are by tomorrow.
All right, great.
Yeah, I want to build on what Dan just said. I'll go back to what I said earlier, which is we have to understand what the disciplines, even in industry, are trying to accomplish.
Yeah.
We're the IT department, like it or not. We provide infrastructure and the best tools to use it. And until they draw a circle around us and say, we couldn't have done it without you, no one's going to really understand. We've got to do a better job of teaming with those people and getting the message out together so that they tell Congress why we're important. It's not us saying, oh yeah, we were there, it was us. It doesn't work that way.
Yeah, yeah. Well, great, guys. I want to thank our panel, and please give them a hand. I think they did a terrific job. Thank you, folks.